When a current-carrying conductor is connected to a neutral conductor, it acts as a return path for the current to flow back to the power source. In this situation, even though connector designation resistor number 2 was not directly connected to the neutral conductor, it was effectively acting as a neutral because it was connected to a conductor connector designation resistor number 1 that was carrying current. This is why the measurement was 120 volts between connector designation resistor number 1 and connector designation resistor number 2, and why connector designation resistor number 2 acted like a neutral. Another way to conceptualize this is that the current flowing through connector designation resistor number 1 creates a magnetic field around the conductor. This magnetic field induces a current in connector designation resistor number 2, which is why voltage was measured between the two conductors. The induced current in connector designation resistor number 2 flows in the opposite direction of the current in connector designation resistor number 1, which is why connector designation resistor number 2 acts like a neutral. To elaborate further, consider the principles of circuit analysis. In a standard alternating current circuit, power is supplied via a hot wire and returns via a neutral wire. The hot wire carries the voltage, typically 120 volts in many residential applications, while the neutral wire is intended to be at or near 0 volts, providing a return path for the current. When the circuit is properly connected, current flows from the source, through the load, and back to the source via the neutral wire, completing the loop. However, when there is a break in the circuit, or a loose connection, the behavior can become less straightforward. In this specific case, with the junction box containing connector designation resistors that had come apart, the intended circuit path was disrupted. When connector designation resistor number 1, which was hot, became disconnected from connector designation resistor number 2, the expected behavior would indeed be for connector designation resistor number 2 to appear dead, meaning no voltage present relative to ground. The surprising result was that connector designation resistor number 2 acted like a neutral, exhibiting approximately 0 volts potential difference relative to ground, and 120 volts potential difference relative to connector designation resistor number 1. This phenomenon can be explained by considering the concept of a floating neutral and induced voltage. Firstly, the fact that connector designation resistor number 2 was not truly at 0 volts, but rather acted like a neutral, suggests that it was capacitively or inductively coupled to other energized conductors in the vicinity. Electrical conductors in close proximity to each other can create capacitance, allowing alternating current to flow through the air gap between them. This is similar to how a capacitor works, where two conductive plates separated by an insulator can store electrical energy. In this scenario, connector designation resistor number 2, being close to connector designation resistor number 1 and other energized wires in the junction box, can pick up a voltage through capacitive coupling. Secondly, the magnetic field created by the current flowing through connector designation resistor number 1 can induce a voltage in connector designation resistor number 2, as mentioned earlier. This is based on the principle of electromagnetic induction, where a changing magnetic field can generate a voltage in a nearby conductor. The amount of induced voltage depends on the strength of the magnetic field, the distance between the conductors, and the orientation of the conductors relative to each other. In this case, the magnetic field created by connector designation resistor number 1, being close to connector designation resistor number 2, induces a voltage in it. The fact that the measured voltage between connector designation resistor number 1 and connector designation resistor number 2 was 120 volts indicates that the induced voltage was significant. The reason connector designation resistor number 2 acted like a neutral is that the induced voltage was such that it created a return path for the current flowing through connector designation resistor number 1. In other words, the induced current in connector designation resistor number 2 flowed in the opposite direction of the current in connector designation resistor number 1, effectively cancelling out the voltage difference between them. This is why the measured voltage between connector designation resistor number 1 and connector designation resistor number 2 was 120 volts, and why connector designation resistor number 2 acted like a neutral. Furthermore, it is crucial to understand that this situation can be dangerous. Even though connector designation resistor number 2 appears to be at or near 0 volts, it is still carrying current and can potentially cause an electrical shock. Therefore, it is essential to take precautions when working with disconnected or loose wires, such as using insulated tools and wearing appropriate personal protective equipment. Restoring the original connection between connector designation resistor number 1 and connector designation resistor number 2 resolved the problem because it reestablished the intended circuit path, allowing the current to flow properly and eliminating the capacitive coupling and induced voltage effects. In summary, the reason connector designation resistor number 2 acted like a neutral when disconnected from connector designation resistor number 1 is due to a combination of capacitive coupling and induced voltage. These phenomena can occur when conductors are in close proximity to each other, creating a path for current to flow even when the circuit is not properly connected. It is important to understand these principles to effectively troubleshoot electrical issues and ensure safe working practices. In addition to the above explanation, it is important to consider the role of impedance in the circuit. Impedance is the total opposition to current flow in an alternating current circuit and includes resistance, inductive reactance, and capacitive reactance. When connector designation resistor number 2 was disconnected, the impedance of the circuit changed significantly. The disconnected wire now had a very high impedance to ground because there was no direct conductive path. However, the capacitive and inductive coupling between connector designation resistor number 1 and connector designation resistor number 2 provided a path for current to flow, albeit a high impedance path. This high impedance path allowed a small amount of current to flow, which resulted in a voltage drop across connector designation resistor number 2. The voltage drop was such that connector designation resistor number 2 acted like a neutral even though it was not directly connected to the neutral conductor. Furthermore, the grounding system of the electrical installation plays a crucial role in this scenario. A properly grounded system provides a low impedance path for fault currents to flow back to the source, which helps to quickly trip circuit breakers and prevent electrical shocks. In this case, the grounding system may have contributed to the phenomenon by providing a reference point for the capacitive and inductive coupling. When connector designation resistor number 2 was disconnected, it was no longer directly connected to the grounding system. However, the capacitive and inductive coupling may have created a connection to ground through other conductors and equipment in the vicinity. This connection to ground may have influenced the voltage potential of connector designation resistor number 2, causing it to act like a neutral. It is also important to note that the specific characteristics of the electrical installation, such as the wiring configuration, the type of equipment connected, and the presence of any nearby electromagnetic fields can all affect the behavior of disconnected wires. In some cases, the effects of capacitive and inductive coupling may be more pronounced than in others, depending on these factors. Therefore, it is essential to carefully consider all of these factors when troubleshooting electrical issues and to use appropriate test equipment to accurately measure voltages and currents. When dealing with such situations, a multimeter is an essential tool. A multimeter can measure voltage, current, and resistance, allowing you to diagnose electrical problems. In this case, the multimeter was used to measure the voltage between connector designation resistor number 1 and connector designation resistor number 2. The measurement of 120 volts indicated that there was a potential difference between the two conductors, even though they were not directly connected. This information helped to narrow down the possible causes of the problem. In addition to a multimeter, a non-contact voltage tester can also be useful. A non-contact voltage tester can detect the presence of voltage without the need to make direct contact with the conductor. This can be helpful for identifying energized wires in a safe manner. In this case, a non-contact voltage tester could have been used to confirm that connector designation resistor number 1 was hot and that connector designation resistor number 2 was acting like a neutral. It is also important to follow proper safety procedures when working with electricity. Always turn off the power to the circuit before working on it. Use insulated tools and wear appropriate personal protective equipment. If you are not comfortable working with electricity, consult a qualified electrician. In this case, the person performing the service call was aware of the potential dangers and took precautions to ensure their safety. They used a volt tester to verify the voltage levels before and after reconnecting the wires. They also knew that it is never appropriate to directly tie a hot and neutral wire together, but they understood that in this specific situation, the two wires were originally intended to be connected. This knowledge and experience allowed them to safely and effectively troubleshoot the problem. Finally, it is important to consult the relevant electrical codes and standards. The National Electrical Code, or NEC, provides guidelines for safe electrical installations. The NEC covers topics such as wiring methods, overcurrent protection, grounding, and bonding. Compliance with the NEC is essential to ensure the safety of electrical systems. In this case, the NEC may provide guidance on the proper methods for splicing wires in a junction box. The NEC also specifies the requirements for grounding and bonding electrical equipment. By following the NEC guidelines, electrical installations can be made safer and more reliable. To further clarify the concept of induced voltage, it can be compared to how a transformer works. A transformer consists of two or more coils of wire wound around a common core. When alternating current flows through one coil, called the primary coil, it creates a changing magnetic field. This changing magnetic field induces a voltage in the other coil, called the secondary coil. The voltage in the secondary coil is proportional to the ratio of the number of turns in the primary coil to the number of turns in the secondary coil. In this case, connector designation resistor number 1 can be thought of as the primary coil, and connector designation resistor number 2 can be thought of as the secondary coil. The changing magnetic field created by connector designation resistor number 1 induces a voltage in connector designation resistor number 2. The amount of induced voltage depends on the distance between the two conductors, their orientation, and the amount of current flowing through connector designation resistor number 1. While the analogy to a transformer is helpful, it is important to note that the situation with the disconnected wires is not exactly the same as a transformer. In a transformer, the primary and secondary coils are intentionally designed to be closely coupled, meaning that a large amount of magnetic flux from the primary coil links with the secondary coil. In the case of the disconnected wires, the coupling is much weaker, and only a small amount of magnetic flux from connector designation resistor number 1 links with connector designation resistor number 2. This is why the induced voltage is relatively small, and why connector designation resistor number 2 only acts like a neutral, rather than exhibiting a significant voltage potential. Another factor that can affect the induced voltage is the presence of any nearby metallic objects. Metallic objects can act as shields, blocking the magnetic field and reducing the amount of induced voltage. They can also act as conductors, providing a path for the induced current to flow. The effect of metallic objects on the induced voltage depends on their size, shape, location, and electrical properties. In this case, any metallic objects in the vicinity of the junction box may have influenced the induced voltage in connector designation resistor number 2. Furthermore, the frequency of the alternating current can also affect the induced voltage. The higher the frequency, the stronger the magnetic field and the greater the induced voltage. In most residential and commercial electrical systems, the frequency is 60 Hz. However, in some industrial applications, the frequency may be higher. If the frequency is higher, the induced voltage in connector designation resistor number 2 would be greater. In addition to the above explanations, it is important to consider the possibility of harmonic currents. Harmonic currents are currents that have frequencies that are multiples of the fundamental frequency, which is 60 Hz in most electrical systems. Harmonic currents can be caused by nonlinear loads such as electronic devices, motors, and transformers. Harmonic currents can create additional magnetic fields which can induce voltages in nearby conductors. If harmonic currents were present in the circuit, they may have contributed to the induced voltage in connector designation resistor number 2. Finally, it is important to emphasize the importance of proper wiring practices. Proper wiring practices can help to minimize the effects of capacitive coupling and induced voltage. Some examples of proper wiring practices include using shielded cables, keeping wires as short as possible, and separating power and signal cables. By following proper wiring practices, electrical systems can be made more reliable and less susceptible to interference. In conclusion, the phenomenon of a disconnected wire acting like a neutral is a complex one that can be influenced by a variety of factors, including capacitive coupling, induced voltage, impedance, grounding, nearby metallic objects, frequency, harmonic currents, and wiring practices. Understanding these factors is essential for effectively troubleshooting electrical issues and ensuring the safety of electrical systems.